What we've got here is a simple electrochemical cell. So recently we've just been looking at electrolysis, which is the opposite of this, where you use electricity to turn a compound into its elements, basically. In this, we're going to use two half cells, an oxidation and a reduction half cell, combined to make a cell, which is going to create electrical energy. Here we've got a zinc electrode sitting in a zinc solution, so no chemical reactions actually occurring at the moment. Here we've got a copper electrode sitting in a copper solution. Again, no chemical reaction is occurring at the moment. They're connected in parallel to a multimeter that I'm going to turn into a voltmeter right now, and we can see that there's no voltage created there at all. This is because the cells are not connected. They're only two separate half cells. So what I've got in this beaker here is a solution of potassium nitrate and a piece of filter paper. I'm using the filter paper because it's very porous, using the potassium nitrate because potassium ions and nitrate ions are very motile, so they can move. This will help complete the circuit or connect the half cells. As soon as I put this in, I should see, hopefully, a voltage on my voltmeter, on my multimeter. Just going to make sure that both parts are connecting, and then we can see 1.05 volts. What's happening now is that one cell has got oxidation and one cell has got reduction occurring. Now I've set this up the conventional way with oxidation on the left and reduction on the right. What we learned in electrolysis is that oxidation occurs at the anode, and that is completely correct. That's still true here for this particular example. So on the left I've got zinc turning into zinc 2+, so oxidation, and releasing those two electrons. Those two electrons then go through the wire and are now available for the copper to undergo reduction. So the copper ions from the solution now are going to have those electrons available to make copper metal. So if we left this for long enough, we'd see that the zinc would start corroding away or disappearing as it gets turned into zinc 2+, and the copper will get more and more copper on it, and the blue solution will start to fade. Well, if these copper ions are being pulled out of solution, then that means that they must be being replaced by something, and this is why we have the salt bridge. The potassium ions get drawn this way to counteract the change in charge over here. We're losing we're losing copper ions, so the potassium ions go into that solution and to replace them. Conversely, the nitrate ions must be going in the other direction. And the reason for this is that the solution over here is becoming more and more positive, so as more zinc ions are made, so the nitrate ions have to go in there to balance the charges out. If it wasn't for the salt bridge, you wouldn't have a completed circuit, so you wouldn't have a cell. You just have two half cells sitting there doing nothing. Now just very quickly, this isn't really using any power, electrical power, or really using any electrical energy. Setting up the multimeter as a voltmeter is measuring the potential difference between the two of them. This half cell has a potential to create a certain number of joules per coulomb or volts, and so does this one. The two together have the potential as a completed cell to have 1.05 volts. Now the actual value for this, if we do it by mathematical reasons, is 1.10 volts, so we're getting a value a little bit lower than what we'd expect. That's not a surprise because we're not doing everything under standard conditions. That'll be talked about in another video. Now just quickly going through some more information we can get from this. Convention is that we have the anode on the left and the cathode on the right, and we have a salt bridge in the middle. So I like to think of it being as simple as A, B, C. And the anode is where oxidation occurs, and you notice that both of those start with a vowel. However, when we're looking at electrochemical cells, there's another cool thing. This is actually the negative terminal of our cell. So you'll see that anode has an N for negative in it. Over here, C for cathode, because it's where the reduction is occurring. Again, we can use the same idea. C and R are both consonants, and so we can use that little thing as a way to remember that the cathode is where reduction occurs. Cathode has a T in it that looks like a plus, which is for positive. The key thing to remember here is that although anode and oxidation, cathode and reduction are always true, here the negative and positive are the opposite to an electrolysis. Now the last thing I want to quickly go through is how we draw the cell diagram for this, and there's a convention for this. The anode itself is made up of zinc, which is a solid. That is sitting in a solution, which is a phase change, so I draw a diagonal line there. And it's sitting in a zinc solution, so that's AQ. Then we've got the salt bridge, which is represented by a double diagonal line. That salt bridge is sitting in a copper 2+ solution, so AQ again. There is a phase change to the cathode, which is there. I think this is explained in another video as well. And again, keeping it as easy as A, B, C, anode, bridge, cathode. Now, if we had something like carbon or platinum as our electrodes and two solutions like permanganate and manganese 2+ in there, we have to draw this a little bit differently. Again, that is covered in some other work.